Hello and welcome to the Maths 2 component of the online BSc program on data science and programming. We are going to start our discussion on multivariable calculus, and to begin with we will study multivariable functions, and we will do a little bit of visualization of such functions. We will see some examples and we will end with by defining what are called curves. Okay. So, let us recall functions of one variable. So, we did this at the beginning of the course. So, recall that functions of one variable are functions from a domain D in R to real numbers. So, they are real valued functions. So, they are like f of x is equal to some expression which is a number, which evaluates to a number. So, here are some examples which we have seen earlier. So, linear functions, polynomial functions, rational functions, and I will remind you of what that was, trigonometric functions, the exponential function, the logarithmic function, and then finally you can take arithmetic combinations of these, meaning you can add them, subtract them. If you are lucky, you can even divide them, you can multiply them, or you could take compositions. So, if your functions are such that the range of one function is contained inside the domain of another function, then you can compose those two functions and you can produce a new function of one variable. So, just to remind you, for rational functions we meant things of the form say x by x squared plus 1. So, this is what typically was a rational function. So, a division of polynomials. Of course, if once you divide, you have to be careful that the denominator is non-zero. If it is 0 somewhere, then you have to say that it is not defined at that point, define it separately, or just say that the domain is a restricted part of the real line. So, polynomials was for example, f of x is x squared plus x plus 1. Linear functions, of course, f of x is a x plus b, where a and b are real numbers, and then trigonometric functions where sine of x, cosine of x, tan x, cotangent x, and so on, cosecant and secant x. Okay. The exponential function was e to the power x, the logarithmic function was log of x. Of course, you have to be careful because log is defined on the positive part. So, we do not define log for negatives. So, here the domain is the positive side of the x axis, and then arithmetic combinations or compositions. So, by this we mean things like log of x squared plus 1. So, this is a composition because you have x square plus 1 and then the range of x square plus 1 is 1 to infinity, which is inside the domain of the logarithm function. So, you do log of x squared plus 1, that makes sense, or you could do log of mod x and it is undefined at 0, or other examples are e to the power sine of x, let us say. So, that is a composition, or arithmetic combinations means something like e to the power x plus e to the power minus x, right. So, these are all functions that we have seen in single variable calculus, and we studied various proper aspects of such functions, things like how do you find maxima, minima, derivatives, continuity, and so on. Okay. So, let us get to scalar valued multivariable functions. So, a scalar valued multivariable function is a function f from D to R. Again, the codomain is R, and that is why it is scalar valued, meaning it takes values in the real numbers. But now D is a domain in R n, where n is greater than 1. Okay. So, this could be R 2 or R 3, R 5, R 20, whatever, right. So, such a thing is called a scalar valued multivariable function, and this is something that we are going to study extensively in the next couple of weeks, and this will show up possibly again in further courses. So, this is mainly what we want to study going ahead. Okay. So, what are examples? Linear transformations, polynomial functions, and I will expound on that in a minute, and then arithmetic combinations or compositions. So, just to be clear of what I mean by linear transformations, you could think of a linear transformation from Rn to R, or define it on some subset. So, for example, you could take something like T of x1 x2 xn is a1 x1 plus a2 x2 plus an xn, right. So, this will be a scalar valued multivariable function. So, we have been thinking of this in terms of linear algebra so far, but now we can think of this also as a scalar valued multivariable function. And well, what's a polynomial function? Well, so you have f of x1 x2 xn, and you can do something like x1 squared plus x2 squared plus xn squared. Maybe another polynomial function is x1 times x2 times up to xn, and then maybe let me add x1 squared x2 cubed x3 to the power 4, and then minus x1 to the power 5 x3 to the power 6. Yeah, so this is an example of a polynomial function in several variables. Okay, and then you could combine these, or you could combine other ones as well, and we will do more examples as we go ahead. Okay, so let us talk about vector valued multivariable functions. So, vector valued multivariable functions means that now instead of R, the domain the codomain can be R m, where m is also larger than 1. So, a vector valued multivariable function is a function f from D to R m, where D is a domain in R n and both m and n are strictly greater than 1. So, such a thing is called a vector valued multivariable function. Okay, so, we can think of this as a vector of scalar valued multivariable functions. Okay. And we have seen the example of linear transformations, which means you can take a linear transformation from Rn to Rm. So, that means for each coordinate you have a linear transformation from Rn to R, right. So, you have linear combinations of your x1 x2 xn, and then you have m many of those. That was exactly how we got linear transformations from Rn to Rm, and we could restrict those to some domain if we want to. So, those will be vector valued multivariable functions. Yeah. So, let me give another few examples. Yeah, f of x y z is x square plus y square plus z square plus x square, right. So, this is a vector valued multivariable function. This is a function from R3 to R3. So, this is another example, and this is not a linear transformation. Okay. So, let us sort of combine these. So, what is a multivariable function? Sometimes this is also called a function of several variables. So, a multivariable function or a function of several variables is either a scalar valued multivariable function or a vector valued multivariable function. So, that means you could have a function from Rn to Rm, or some domain in Rn to Rm, and here we insist that the n is bigger than 1, but there is no restriction on m. So, m could be 1 or m could be larger. Okay. If it is larger, then that will fall under the category of vector valued multivariable functions. If it is 1, it falls under the category of scalar valued multivariable functions. So, we will not distinguish between these when we say just multivariable function. If there is a reason to distinguish, we will make it explicit. Okay. But much of what we are going to study is scalar valued multivariable functions. Fine. So, just as to set notations as we go ahead, if we want to refer to an element in D, what is D? D is this domain in Rn without bothering about the coordinates. So, remember that n, since we are in Rn, we have coordinates x1, x2, xn, but sometimes we do not want to explicitly talk about coordinates. We just want to let us say if I want to add two functions. So, f plus g of x1, x2, xn. So, this I do not want to refer to x1, x2, xn. So, I will just refer to x tilde as x1, x2, xn. So, this is the vector x1 x2 xn or the n tuple x1 x2 xn, whichever is convenient for the purpose at hand. So, do not get confused if you see an x tilde, it just means x1 x2 xn. Okay, so, with that caveat, let us look at lots of examples. So, here is a linear function. So, this is a scalar valued function from R2 to R, 2.5x minus 3.9y. Here is a polynomial. So, 2x cube minus 3y squared plus 4.8 x squared minus x squared times y minus 9.9 xy plus pi. Here is a slightly more complicated function, sine of x squared plus y squared. Here is an example that you may actually have seen in statistics. So, this is f of x y is 1 over 2 pi e to the power minus x squared plus y squared divided by 2. So, this is the bivariate normal distribution, in case that rings a bell. Another example may be from statistics. So, this is f of x y is 10 times e to the power minus 2x minus 5y. You can think of this as bivariate exponential, or you can think of this as two independent exponentials and the joint density of that. Then here is a rational function x y divided by x squared plus y squared, and do keep this in mind because we may come across this again as we go ahead. Okay, let us continue with our examples. So, here is f of x y z is x squared plus y squared plus z squared. So, again all of these are scalar valued functions. So, they are taking values from R2 to R or R3 to R. This is from R3 to R. So, here is an example of something which is not a scalar valued multivariable function. This is from R3 to R3. So, f of x y z is 2x comma 2y comma 2z, and these two examples have something to do with each other, and we will encounter them later on. And just as a more convoluted example, here is f of x y z is sine of x times cosine of y, comma tangent of y plus z, comma logarithm of x squared plus y squared plus z squared. Again, this can't take values when x y z is 0 and all three are 0. So, we have to define this function a priori on the domain where x is not 0, y is not 0, z is not 0. Of course, we also have a tangent of y plus z. So, we have to define this when tangent function there are it does not exist everywhere. So, we have to be careful that y plus z is not multiples of odd multiples of pi by 2, right. And then we have e to the power x y z in our last coordinate. So, this is a function from some domain in R3. So, this is defined in some domain in R3 and its range is in R4. So, its codomain is R4. So, this is a function of this f is from D to R4. So, just as an example. So, you can see here that we have got this by taking various products and compositions and so on of well known functions, functions that we understand well. And I will also maybe mention a couple of other examples that so sometimes you may be we may be interested in defining functions piecewise. So, it may have some definition on some part and some definition somewhere else. For example, you could have that f of x y is 1 on the unit interval. So, x y or maybe I should write this as when x and y are both between 0 and 1. So, this is on the unit square and it is 0 otherwise. And this is something you may have seen again in the statistics course. This is the uniform density on the unit square. And there could be other piecewise definitions. For example, you may have f of x y is let us say x times y and 0. This is on some part x y is in D, and if it is not in D. Yeah. So, we have functions of this type also. So, they may be defined piecewise. So, of course, here when we say piecewise, the piece refers to a piece of Rn, meaning the domain Rn. So, in this case the domain is R2. So, it refers to pieces of R2. So, now do not think of pieces as intervals in R, instead think of them as sets on the plane. If you have R2, if you have Rn, of course, the visualization is much harder, which leads us to an important point as to how do we visualize such things. So, let us do examples of that. So, of course, visualization for multivariable functions is much harder than it is for functions of one variable, and that is because to visualize we have to think of the graph. And if you remember what the graph was, the graph meant it is a subset of the domain cross the codomain. So, in here the domain is Rn and the codomain is Rm. So, it will be a subset of Rn cross Rm, and of course, our visualization is limited to 3 dimensions. So, unfortunately, we can't visualize functions which for any n and m, but if n is 2 and m is 1, so meaning functions from R2 to R, such functions or subsets of R2 to R, such functions we can visualize. Okay, so, let us do some examples of those, some of the functions that we have seen in fact. Okay, so, here is a linear function. The function f of x y is minus 0.9 x minus 1.5 y. In fact, this function is f of x y is a times x plus b times y, and this a and b are varying in an interval. So, if I play the slider, the function will change, and this looks like a plane. So, this is a plane. So, linear functions, the graph looks like a plane. This is something we understand, because this is exactly the plane. Z is equal to ax plus by. Okay, and how does this plane move? So, if we animate it, so this is what happens to the plane as a and well, we can animate b as well. So, if a and b both change, this is what happens. So, this plane moves around depending on the coefficients. Okay. So, let us look at the example of a rational function. So, the rational function that we had as an example in our slides was f of x y is x y divided by x squared plus y squared, and here is how the rational function looks like. So, this is yeah, it's some kind of surface, and as you can see there is some strange thing happening at 0, because at 0 this function is a priori not defined. So, but what is worth noticing is what happens around 0. So, if you look at this side and this side, it is looking like you have hills, right? The function is like this, whereas if you have the other two sides, then the function is like you have troughs. Okay. So, such phenomenon is very interesting, and we will try to detect such phenomenon as we go ahead. Okay, let us look at another interesting function. So, this is the function sine of x squared plus y squared. Okay, if we plot the graph, well, here is what it looks like. So, if this is the projection down to the down to R2, this is what happens. So, it's you can see it's oscillating, right, because the sine function oscillates. So, depending on the value of x squared plus y squared, the sine function will take some value. So, it will move in circles. So, as your circles go out, that is how it looks, and this is how it looks if you view it over the plane R2. So, this is something in R3, and you can see it is moving in circles, right, as your circle. Yeah. So, this is the origin. So, at 0 0 it is 0, and then as x squared plus y squared the radius increases, you get that it increases, and then as the radius is pi by 2, that's when sorry, root of pi by 2. So, x squared plus y squared is equal to pi by 2. That is when it attains 1, and then it goes down again. So, again at pi it becomes 0, and that is how the behavior continues. Okay. So, so this is a very interesting function. Yeah, it looks very nice. Yeah. So, as you can see, graphs of functions can yield some very beautiful visually appealing pictures. Okay, let us now look at the example of the exponential joint density of for two exponential two independent exponential random variables, and so here the means are 0.86 and 3.37, and as we change them, the picture will look different, and this is how it looks like. Yeah, this is the exponential function. So, as you can see, it's very sharp, and then it goes down to 0 very fast, right. So, this is exactly what happens for the one variable exponential function. And finally, let us do the example of the bivariate normal. So, this is how the function looks like. So, it is an exponential function, but it goes down to 0 very fast. The only around the origin there is a hill, and the size of the hill depends on some parameters like the means and so on, and so this will show you how it changes. So, depending on how it couples or how the means are, it will be a very steep hill or it will be a much flatter hill, but it will always be a hill, and for most of the plane it will be very close to 0. Okay, so, having seen some examples, let us return back to our slides. So, let us do the same things that we did for one variable functions, namely we can let us note that we can perform arithmetic operations on these functions. So, if you have two functions on the same domain D, so you have f and g from D to R m, and both of which are multivariable functions on D, then you could, for example, add them. How do I add them? So, if you want f plus g of x tilde, then that is f of x tilde plus g of x tilde. This makes sense because in R m you can add vectors, right. So, R m is a vector space in particular. So, this is one of the reasons why we specifically studied linear algebra. So, suppose you have a constant c, so scalar, then the function c times f is defined on D by c f of x tilde is c times f of x tilde. So, what does that mean? Again, this is scalar multiplication in R m. So, that means it multiplies each component in R m, and if m is 1. So, this is a case of scalar valued multivariable functions. Then we can even talk about the product. So, the product function f g is defined on D by f g of x tilde is f of x tilde times g of x tilde. This makes sense because you can multiply real numbers. So, the same way as we did for single variable functions, you can do this for scalar valued multivariable functions, and for the same reason you can also divide, but provided the denominator is non-zero. So, if you have a scalar valued if m is 1, meaning f and g are both scalar valued multivariable functions, and g of x tilde is non-zero, then the quotient f by g is defined, and f by g of x tilde is f of x tilde by g of x tilde. And for so basically it is defined on the domain D except the points where g of x tilde is 0. So, it is a smaller domain than, it could be a smaller domain than D. Okay, let us continue and talk about composition. So, if you have functions let us say a function f from D to R m, and you have another function g from E to R p, where what is E? E is some domain which contains the range of f. Okay, so, the range of f is contained in the domain E. Then we can talk about G composed f, right. So, for each x tilde in D, we can talk about G composed f by looking at f of x tilde and then applying G on that. Why can we do that? Because the range of f is contained in E. So, f of x tilde is contained in E. So, G of f of x tilde makes sense. So, this yields a well defined element in R p. So, we can talk about G composed f. So, this is called the composition. So, we will not have a lot of use for this when m and p are beyond 1, but for the cases where m and p are both 1, we have already seen examples of this. For example, we had sine of x squared plus y squared. So, x squared plus y squared is a function from R2 to R, and then we have a function from R to R again, which is sine of z. So, we can apply that on x squared plus y squared, or we had logarithm of x squared plus y squared plus z squared. Of course, this works only for the positive side. So, x squared plus y squared plus z squared, we have to restrict for non-zero x, y, z. Okay. So, here is an example, f of x y is x squared plus y squared is a function from R2 to R, and then we could look at g of x is square root of x. So, this is a function from the non-negative part of the real line to R. So, you can do g composed f, and that gives us square root of x squared plus y squared. So, this is a function that we would like to understand. This is like the radius, if you think of x squared plus y squared as being r squared, where r is the radius. Okay. So, finally, I am going to end with something which is slightly off topic, but this is one for the sake of completeness and because we will have some use for this in what is coming. So, this is curves in Rm. Okay. So, we have studied multivariable, we have studied single variable functions, which is R to R. We have studied multivariable functions, which is Rn to Rm, where n is strictly greater than 1 and m could be 1 or more. Okay. So, that leaves us with one case, which is n is equal to 1 and m is bigger than 1. That is exactly this case here called curves in Rm. Okay. So, a curve in Rm refers to the range of a function f d to Rm, where d is a domain in R. So, it is a function from some subset of R to Rm. So, we have seen such examples before. So, just to recall, let us look at lines in Rm. So, for example, if you have a line in R2, that is an example of a curve. Gamma of f, where f is a function of one variable. So, this is a curve. In fact, we did talk about general curves in at least in R2 when we were talking about tangents earlier. Okay. So, gamma of f, where f is a function of one variable, this is a curve in R2. Well, actually, if it is a function of one variable with range in something else, then gamma is then also gamma is a curve. So, conics in R2, this is very a very important example. So, conics in R2, again we have talked about these when we did tangents. So, this is for example ellipses, parabolas, hyperbolas, the circle, right. And then here is two more examples. This is one of my favorite examples, the helix in R3. So, that is cosine t comma sin t comma t. So, this is a parametric equation. So, as t varies, this vector cosine t sin t varies, and how does it vary? It varies like this. Yeah. So, this is the helix, and as you may have heard, the helix is used in various branches of science, including biology. So, this is like the slingy. Yeah, we have this thing called a slingy like this, and then you throw it, it is like a wire, then when you throw it, it kind of bounces from step to step, right. That is exactly how the helix looks like. Okay. And finally, just for the sake of completeness, here is the subset x y such that y is equal to x cube. So, this is a subset of R2, and I will encourage you to draw this subset and see how it looks like. So, conics in R2, let us give a couple of examples of that. So, one example is x squared plus a squared plus y squared by b squared is 1. So, the ellipse, and a special case is when a is equal to b, that is the circle. So, x squared plus y squared is equal to a squared, or we have things like x y is 1. Okay. So, yeah, these are examples of conics, and I want to make a point here, namely that see this, there is a slight difference in the representation that we have here, whereas as opposed to the representation we have here. This is called a parametric representation, s of t is equal to cosine t sin t t, because we are describing the curve in terms of a parameter t, whereas these two are as sets. So, they are we are giving the defining equations. Of course, it is quite often one can go between the two. So, we can parameterize this. For example, for if you have x squared plus y squared is a squared, then we know that a parametric equation is a times cosine theta, a times sine theta. Yeah, more generally, if you have x squared by a squared plus y squared by b squared, you could have a cosine theta, b sine theta. So, you can go between parameters and equations, and sometimes it is useful to do that. Okay, so let us just summarize what we have seen in this video. We have seen multivariable functions. In particular, we have seen scalar valued multivariable functions and vector valued multivariable functions. We saw that we could do arithmetic operations on these, specifically addition and subtraction, and when they are scalar valued, you can actually multiply and divide as well. And then if you have two multivariable functions such that the range of one and the domain of another matches up, then you can compose them as well. That gives you a new multivariable function. Finally, we saw curves. We also saw a bunch of examples where we visualized these multivariable functions. Thank you.